Hi there, guys. Well, we're working on 4M from the book now, and that's about graphical interpretations of the derivatives. And we talked a little bit about this at the start of the previous video, and that might be worth looking through again. We're talking about how derivatives, the first and the second derivative, relates to specific graphs or curves of graphs which we have. So there's a little investigation here to start off with, but this is also perhaps could be defined, this exercise, as being about turning points, extrema, turning points, stationary points. That's what they're talking about, maximum and minimum points within functions. Okay, so again, I'm just going to do a little bit on that. Just going to do a little bit on this. What we talked about in the previous one is actually about the second derivative as well. But this exercise is all about the first derivative. Now, in terms of the first derivative, it's really easy to see that up until this point here, we've got positive gradients. Okay, so this is f dash of x for all x that you choose there up until this point is going to be greater than 0. Now, at this point, we can say f dash of x is going to be equal to 0. So in other words, when we have an instantaneous gradient which is equal to 0, then your derivative is going to be equal to 0 as well. If the gradient of the tangent is 0, we must have a turning point. Okay, or we just have a completely flat function. We have some sort of flat piece, but we definitely have a gradient of 0 at that particular point, which indicates that we have a local maximum or minimum turning point. Now, maximum points are like hills, minimum points are like valleys. Now, these are also called stationary points. They're called stationary points because the gradient is 0 at that point. Okay, now up until this point here, you can see in this section, we've got f dash of x is greater than 0. So for any x, not greater, sorry, is less than 0. So for any x that we choose in here, we can see that we're getting negative gradients out. Okay, and then after that, of course, we're getting positive gradients out. Okay, and so there you go. Got this section here, we're saying again, we've got f dash of x is greater than 0 again. And at each of these points here, each of A, B, and C, you'll have f dash of x is equal to 0. And then, of course, you can see f dash of x is less than 0 for this last section. Okay, so in the previous video, at the start of that, I also talked about second derivatives, but I'm not going to do that here because that's going to turn up in the next exercise as well. Now, in terms of the way this book talks about it or defines things, it comes up with this, and this is really, again, this is another one of those boxes which is pretty unpleasant to read, but actually this one is saying something which is fairly obvious, so we can go through this really quickly. Now, at the top it says a global maximum or minimum of a function is the greatest or least value function attains in its domain. True, in its domain, but I mean, you could say, well, look, I mean, in this case, there's the domain. So is this a maximum turning point? So is this one, or is this maximum turning point? Well, this is the global one because it's in the entire domain. So that's the highest point of the entire domain. Now, local maximum or minimum points are these points here. So we normally just call these turning points. We'll say this is a maximum turning point, but you can also say it's a local maximum point. That means to say, if you just take a small chunk of the domain around it, it's going to be a maximum in that domain, but there's possibly a higher point overall in the function. Okay, so global maximum could be this. Now, when we look at this function which I've just drawn out here, if this and this is the sort of the section of our domain which we're considering, then the global minimum in this case is actually going to be here. It's not going to be a turning point. It's going to be the point which is at the end of the function. So you've got to be really careful with these, that sometimes global maximums or minimums are not turning points. Often they are, but sometimes they're not. this is the lowest value overall in this function. This would be your global minimum. So sometimes global maximums and minimums are not turning points. I suppose you could say that in this case here, if we took this as our domain, like from there to there, this would be a local minimum there as well. So minimums aren't necessarily turning points, but we're mostly focused on turning points. Okay, now in terms of this box, let's make a little sense of it then. It says f has a turning point if and only if f dash of x is equal, f dash of c is equal to 0. Okay, now is that true? Now is that true? If and only if? Definitely if f dash, if there is a turning point, then f dash of c is equal to 0. But what about the function? What about the function f of x is equal to 2? There's no turning points there. And you know, or for example, sorry, because that's not giving us it's equal to 2. No, that would work. Sorry, f dash of c there would be equal to 0. You know, so we're talking about non-trivial functions here. Okay, so there you go. So turning points basically have f dash of x is equal to 0. And if f dash of x is greater than 0 up until the point, and if it's less than 0 after the point, you know, so if it's if f dash of x is positive up until the point, and if it's negative, that's what it's saying here, gradient is negative after the point being at x is equal to c, then we can see that there's got to be a local maximum here. This is a local maximum point. And you know, the opposite is true for getting a local minimum. So we can look around that point and we can say, well, is this turning point, which we found, a minimum or maximum? If it's a minimum, then the gradient is going to be less than 0 before the point and greater than 0 after the point. Now, to be honest, all of this stuff here, I wouldn't really use that. I'd use the bit which is turning up in the next exercise, which is to talk about the second derivative. The second derivative, in this case here, is always going to be greater than 0 because the gradient is increasing throughout. So we can just check at a particular x point, if we put in x is equal to c, and find out that the second derivative is greater than 0, then we know that we have a minimum turning point. Okay, that's turning up next, but you might as well know that now. And then it says if f of x is continuous and differentiable on this interval, and if f dash of x is greater than 0 for all x in this domain here, so from, it's just saying, of course, this thing here with the brackets facing the opposite direction is just saying x is trapped between a and b, then it's saying that we have an increasing function. Now, sometimes you ask, do you have an increasing function here, all values of x? And you'll need to prove that this function f dash of x is greater than 0 for all values of x. Say, for example, if f dash of x is equal to x squared plus 2, we know that this is always greater than 0. Therefore, we know that we have an increasing function. Okay, and again, there's the opposite is true for the last bit. Okay, well, not a particularly nicely worded thing, but, you know, important all the same. And, you know, we do have to sort of get through these definitions. Okay, so example 26 says find any turning points. So that's nice and easy. That's setting f dash of x is equal to 0. And that's saying, well, okay, we're putting, well, we actually have to work out what f dash of x here is, what is as well. And the 1 disappears because it's just a constant. And then we're getting out minus 8x and plus 8 to the power of x cubed. And again, we can just divide through by, 8, we could divide through by minus 8, in fact, and we're going to get x cubed minus x is 0. Factorize out your x. Don't, in this case, divide by x, because if you divide by x, it's possible that x is equal to 0 is a solution, and we'll lose that if we divide by x. So factorize when you can. Now, we've got x and x squared minus 1. We can see that that one factorizes further, of course. So we're getting x minus 1 and x plus 1 there is equal to 0. Find any turning points? Well, this is implying that x is equal to 0, in order, minus 1, 0, and 1, just the solutions to this equation. Okay, what makes the brackets equal to 0? But determine the nature of the points and justify your answers. Okay, now we don't know, or we're not meant to know at least, that we can use the second derivative here. I really would do that, but if the question is forcing you to do this through some sort of sign table, well, by considering f dash of x, and it can say by considering f dash of x, then unfortunately we're going to need to see where this function has positive or negative gradients. Okay, so we know on our axis that we have minus 1, 0, and 1. We need to check this region, this region, this region, and so on. Okay, now, however, okay, a few videos back, I talked about the shapes of graphs, and we know cubics look like this, have a maximum of 2 turns, or this if it's a negative cubic, and a quartic looks like this if it's a positive quartic, not necessarily symmetrical. Okay, so it looks like this if it's a positive quartic, and looks like this if it's a, here we go, negative quartic, and or potentially a quartic could look like that, but we're talking about the maximum amount of turns that it can have. Now, since we know that it goes through the x-axis several times here, we know that it actually has the maximum amount of turns. And so, of course, it has 1, 2, 3 turns. It's going to look like a W this because it's a positive quartic. So actually, I know already what this one's going to look like. It's going to look like, oh, hang on a second. All right, okay. Yeah, okay. So these aren't my roots to the quartic. These are my, these are my roots to finding out where my turning points are. Okay, so somewhere or other, here, and here, and here, okay, somewhere there we have turning points. Now, I'm not sure where they are in terms of the axis, but we have these turning points, but I definitely know that this function, okay, this function here is going to be, now this is going to be a cubic and a positive cubic, so this function is going to be like this. Okay, so that's our cubic. Now, I don't know where the heights of my quartic are, but it's possible, for example, it could be like this, and like this, okay, and like this, and like this. That could be my quartic, for example. Okay, but I definitely know this is the case for my cubic. Okay, that's my cubic. That's me plotting my first derivative. So I know that I'm getting answers here for my cubic, which are, there we go, negative, meaning to say that I've got a negative gradient for my quartic at that point. Okay, and there we go. And there's an example of a quartic which it could be. And then in this section, I know that this is positive. We're getting positive answers for the gradient here. This is the gradient function which I'm plotting. Okay, the gradient is positive in between here and here. Now I can see from this section, I can see that the gradient is negative between 0 and 1. Okay, and then I can see after this that the gradient is positive. Therefore, what are the nature of my turning points? Well, here I have a minimum turning point because up until -1, I have negative answers to my gradient. So I have a negative gradient and then a positive gradient, meaning to say that I have a local minimum. Now, if I have positive followed by negative, that means I've got positive followed by negative on my f of x example. Okay, and this is f dash of x exact, actual. Okay, and so between, what are we saying, between here and here, okay, we're going from positive to negative. That means we've got a maximum turning point. And then from negative to positive, again, we're going from negative to positive is going to give us a minimum turning point. Okay, now somehow you're going to need to find a way of presenting that in a nice, neat way. Now, it's possible that you could actually, if you haven't drawn out this f dash of x, it's possible that you could just, for this line here, you could try putting in numbers into this function, seeing whether you get positive or negative answers. For example, you could try putting in -2, and you'll see that you'll get a negative answer here. You can try putting in -0.5, and you can see then that you're going to get a positive answer. Okay, so the way in which the book does it, because this is getting super scruffy, is they say, well, here we go, here's a sign table. So they're giving you this table here. Let's just steal this whole thing. Okay, so they're giving you this sign table, and they're saying, well, look, a bit better than what I've done. They say, well, what's happening when x is less than -1? What's happening in between? What's happening between 0 and 1? What's happening when x is greater than 1? Okay, well, the f dash of x is less than 0, is greater than 0, is less than 0, and is greater than 0. But now we still need to say, and not only are these the turning points, we still need to say, okay, well, from positive to negative means we have, sorry, from negative to positive means we have a maximum turning point, max between these two. From these two, from positive to negative, we have min. So, you know, positive to negative. No, we don't. We have max. I'm messing up here. Sorry. Minimum. This is why it's always good to draw it out. Negative to positive, minimum. We've got maximum. Okay, so we've got positive to negative, maximum. And between these two, we've got minimum, okay, a minimum turning point. Now that's an awful lot of writing out. And still we haven't clarified this clearly to the examiner. But again, it's going to be quicker when we use the second derivative. Okay, and so they haven't finished this one here. So that's what they're writing. And they're just giving an explanation to this. They're saying, since the gradients go from negative to positive through the point x is equal to -1 and x is equal to 1, then we have minimum turning points there. And since the gradients go from positive to negative, then there's a local maximum. Well, again, just a reminder, we definitely know this is a positive quartic, so we definitely know we've got minimum, maximum, minimum anyway. So, you know, the fact that we're having to do this to show that it's the case, just drawing a picture of the graph is not going to be good enough here. So the fact that we have to do this kind of, that's long work, frankly. Okay, then it says state the intervals in which the function increases, decreases. Okay, so again, we've got the shape of this graph, and now a graph is going to be useful here. And we can see that up until here, the function decreases. In between these 2 points, the function increases. Between the next 2 points, it decreases, and then afterwards it increases again. So I think you could say for part C that simply because we are being asked to state, we can say that, I guess to remember this is -1, 0, and 1, that when x is less than -1, and also when x is trapped between 0 and 1, we have decreasing function. So we have a decreasing function. Okay, and then for the other one, so when we've got the other two intervals here, so when x is trapped between -1 and 0, and when x is greater than 1, we can see that we have increasing functions. So then we've got our increasing function. Sorry, running out of room there. Okay, now in the final part of this, it says confirm your answers graphically and state whether the points found in part A are a local or global extrema. Now, we can see that these are, we're going to need to have this graph here, and we can see we can use the calculator, so they're expecting us to use GDC. Now, it would be quite easy to sketch this graph as well, because if we put in x is -1 into this function here, and we don't have access to our GDC, then we can find where this turning point is. If we put in 0, we can find out where that turning point is. If we put in 1, we'll find out that turning point, and then we just need to join the points together. And it's easy to see as well that it's going to cross the y-axis at 1, and I don't know where this crosses the x-axis because we haven't done this is equal to 0, and we're not asked for that, so I wouldn't stress about that. But normally in sketches you do show where our x-axis intercepts are, but you know, it depends on what we're trying to show and what we're trying to demonstrate, really. So let's have a look at their graph. There we go, that's their graph. You can see they've done an awful lot of writing, like what's looking like complicated writing out there for C, but really, again, as long as you write something sensible, it's fine. And then D, this is your graph. Okay, and we're verifying what we have here, and we can see that we've got 2 global minimum points. They're the minimum points in the entire function. We have a local maximum at this point here, and then the graph just continues on both sides. This is valid for all R. We're not restricted in our domain here. If we were restricted in our domain, then we could note what our other global maximums are. So this would be a global maximum, or this would be if we restricted the domain, but they're not asking for that. They're just asking for the turning points. What type of points are they in this function? Okay, this one happens to be symmetrical, by the way, and they're not all symmetrical. You know, you could have quartics which are looking like this. Okay, well, let's look at the next bit. Well, there isn't another question. It's just 4M next. And there's 7 questions there. And there we go, that's done.